Good morning, Year 11 Science students. Today's work is going to be on drawing distance time graphs and interpreting them. So you'll won't have to plot all of them, but you will have to be able to work out what the different slopes and the lines mean in regard to how objects are moving. This one here is about a particular mouse. So this is the start of the journey. This is the distance axis, and we need to give it a unit, so it's going to be meters, distance in meters. This is time in seconds. So we've got a journey for this mouse that was 16 seconds long, and the total distance was 16 meters, is what it travelled. Now, looking at this first part, this is called section A, from there to there. It's travelled 2 seconds, and it covered 2 meters for that bit. Because it's a straight line being ruled, that means that it's travelling at a constant speed the whole time. When it gets to this section here, you can see that from 2 to 5, so that's a period of 3 seconds, it did not travel any further. Its distance there is 2, and its distance there is still 2. Same distance from the start. Therefore, for that bit there, it was stopped. Then it came to here, and you can see that this line here is much steeper than that one. This means that the constant velocity for this period here was a higher constant velocity than for that period. So you can calculate that and work it out by going, you can see that it's 7 minus 5, so it's a 2 second period, just like it was there. But this time, instead of only travelling 2 meters, this time it's gone from 2 all the way to 6, so it's travelled 4 meters. This line here is actually twice as steep as that line, which means it's travelling twice as fast. Then we get to section D, and you can see it's another horizontal line. That means, again, it is stopped. There's no movement there. And then we get onto this one. You can see the slope of this line is not as steep as that one, but it's a bit steeper than that one. So it's a constant velocity again for that period there, but not as fast as that one. Then for F, we've got a little bit section here which is being ruled. So that section there, up until that cross, is stopped. The mouse stopped moving. This period here of a curve, that shows that at the start of the gradient's not very steep, which means it's not going very fast. But towards the end, it gets steeper. The slope gets steeper, so it starts to travel faster. This section G is acceleration. That means it started moving. Hitting my clamp. It started moving at a slower speed than what it was when it finished. So it was speeding up the whole time. So that's another 2 seconds from 13 through to 15. Another 2 seconds, it was accelerating there. This section here is the fastest bit of movement by the mouse, where it was going, because it's the steepest line. Section I put on there, just to point out that you will never see a vertical line on a distance time graph, because this means that it was actually simultaneously if we look across, it's simultaneously at 16 meters and at 18 meters at the same point in time, which means it moved 2 meters instantly, which is not possible unless you're traveling at the speed of light, which brings in a whole lot of other problems. So you won't see a vertical line on a distance time graph. Alright, one of the other sections later on, I think it might be coming in at page 16, you have to start doing some calculations around these graphs. So if we calculate the velocity for section A, you'll see that, so we'll write this here as section A. Change in distance is going to be 2 minus 0, and the time is going to be 2 minus 0. So therefore, the velocity is 2 divided by 2, 1 ms minus 1. And you can work out the unit because we've got meters here and we've got seconds here. So it's meters divided by seconds. So ms minus 1, it's the unit for velocity. It will always be that. One other thing I'll point out is with these graphs, time always has to go on the horizontal, because on the equations that we use, time is on the horizontal there. So that's why on the graph, time is on the horizontal and time is on the bottom of the equation. If we jump to another section, maybe we'll have a go at section c, for example. So here's c. Find the velocity. Same formula. Distance divided by change in time. The change in distance here is 6. Take away 2. Put it in brackets. And then we're going to work out the time. So that's 7. Take away 5. Then we simplify it. 6 take away 2, that's 4. 7 take away 5, that's 2. 4 divided by 2, so 4 chopped into 2 pieces, gives us 2. The unit here again is ms minus 1. So you can see that's what I pointed out at the start. It's twice as steep, therefore it is travelling twice as fast. If you've learnt gradients in mathematics, then you will be familiar with the fact that gradient, so that just means the slope of the line. Gradient is, the symbol for that is lowercase m, which is equal to rise over run, or change in y over change in x. And on our particular graph here, on our y-axis, so this is our y-axis, we've got change in d. On our x-axis, so this is x down here, we've got change in time. So we've set out our equation to match the gradient calculation. That means that the gradient is equal to velocity. If we wanted to check the velocity for maybe section D, for example, should just be able to fit it down here. So for section D, if we want to find the velocity, then we write down our equation. Velocity is change in distance divided by change in time. The change in distance here is going to be 6. Take away 6. And we're going to divide it by the time, which was 9. Take away 7. So we end up with 6 minus 6. So that's 0. 9 take away 7. That's 2. 0 divided by 2. That's 0. ms minus 1. So that's how we can prove with a formula that it is stopped. Got 0 velocity there. Works for there and for there. I hope that this worked out well for you.